Alrighty guys, tonight we're going to be talking about half-life. So decay and half-life. Now, an unstable element, you guys know this, you've heard me say it many, many times. An unstable element is going to decay via either alpha, beta, or gamma decay, or a combination of the three, in order to reach stability. And this decay is going to happen due to probability, and that's the probability that a particular isotope of a particular atom has to decay. So it's going to happen based on probability. Whether one atom of a substance decays is based on probability. And this decay will happen over a specific amount of time called the half-life. And what I mean by probability is that if I have a sample of, say, carbon, I can't predict or make one atom of that carbon mass decay over another one, okay? The probability of one atom decaying versus another atom it's just that, it's probability. So it cannot be determined or made to happen. So that's kind of just something to think about. Now, the half-life is described as the amount of time it takes for a particular isotope of an element to lose or decay away half of its mass. All right, so if I start with 10 grams of unobtainium, okay, fake element, if I start with 10 grams of unobtainium and its half-life is 2 minutes, after 2 minutes, I'll only have 5 grams. After 4 minutes, I'll have 2.5 grams, and so on and so on and so on, where I lose half of its mass through each half-life. But there's always some sort of fraction of the sample remaining. You will always have the sample. It can't decay away forever. It can just decay away towards background. Different isotopes have different half-lives. And so that means different elements have different half-lives, and different isotopes of elements have different half-lives. And half-lives can range from fractions of a millisecond to billions of years. So here's an example table of some half-lives that are known. Copper-64, for example, has a half-life of 9.67 minutes. Okay, so it's a pretty short half-life. Plutonium-240 has a half-life of 6,563 years. Plutonium-239 has a half-life of 24,110 years. Okay, so they're both plutonium, but that's a really large difference, 65,000 or 6,500 years versus 24,100 years. It's a pretty big deal. And then uranium-235 has a 7.03 billion, right? Million year half-life. So 703,800,000 year half-life. It's got an incredibly large half-life, which is good for fission. So something that you want to have a long half-life would be stable for a longer amount of time. It's something that you don't want to go away. Something that has a short half-life is going to decay away really quickly. And so if you have a contaminant somewhere, you'd hope it would have a short half-life. The half-life equation. Alright, it's N is equal to N naught times 1 over 2 to the T, where N is the amount of isotope at the end, and naught is the amount of isotope at the beginning, and T is the number of half-lives, okay? And we're going to utilize this equation, and it's not going to be terrible. I know you seem terrified of it, but it's not going to be that bad. So let's plug it into an equation. So knowing the half-life of an element means that you can actually predict the amount of an element that will be present after a given amount of time. So for example, if I start out with 250 grams of carbon-14, which has a half-life of 5,730 years, how much carbon-14 will I have after 17,190 years? So, in order to do this, we need to figure out the number of half-lives so that we can plug it back into our half-life equation. And then a way to figure out the number of half-lives that have transpired is to take the amount of time that's transpired, in this case 17,190 years, and divide it by the half-life, which in this case is 5,730 years. So when you do that, you see that 3 half-lives have passed by. So I'm going to plug that number in as T into my equation. N is the number I'm solving for, how much C14 I will have at the end, and O would be my 250 grams, how much C14 I had at the beginning. So N would be equal to 250 grams times 1 over 2 to the 3, because I experienced 3 half-lives. So N, when I plug this into the calculator, is equal to 31.25 grams. Now, another way to look at this is to say that if I start out with 200 grams, after 5,730 years, I'm going to have 125 grams. That's one half-life. Another half-life passes by, so 11,460 years later, I have 62.5 grams. That's 2 half-lives. And after my third half-life, 17,190 years, I only have 31.25 grams. So I divided my mass by 2 for each half-life. So 250 divided by 2 is 125, divided by 2 is 62.5, divided by 2 is 31.25. Now, the other thing that you can do with this is to rearrange the equation, and you can, if you know how much of an element you started with and how much you currently have, you can determine its half-life. So an initial amount of 45 grams of Seaborgium-106 decays away until only 0.703 grams remain, and that happens in 11.64 hours. What is the half-life of Seaborgium-106? So in order to solve that, I'm going to plug it into this equation, but I'm going to solve for T now instead of N. So where N is my my final amount of Seaborgium-106, so 0.703 grams. 45 is my initial amount of Seaborgium, and that's 1 over 2T. If I divide both sides by if I multiply both sides by 2 to the T, I get 2 to the T is equal to 0.703 grams, which is equal to 45 grams. If I divide both sides by 0.703, I can get 2 to the T equal to 45 divided by 0.703. And now, to isolate T, and I can't remember what math you learned this in, but I'm going to tell you the process now and you'll be able to use it. If I take the natural log of an exponent, the exponent comes down in the front. So if I take the natural log of both sides, I get T times the natural log of 2 is equal to the natural log of 45 divided by 0.703. To isolate T, I'm going to divide both sides by the natural log of 2, which 45 divided by 0.703 is around 64.01. So the natural log of 64.01 divided by the natural log of 2, plug that all into the calculator, and you get T is equal to 6, or 6 half-lives. Now to figure out how long the half-life is then, I take the number of hours that have transpired, 11.64 hours, and divided by the number of half-lives equals 1.94 hour half-life. Okay? Utilizing this equation, you can do a variety of things. You can figure out the amount of isotope that you're going to have at the end. You can figure out how much you had at the beginning. You can figure out the number of half-lives. You can figure out the half-life. You can do many different things to figure out. This is how carbon dating works, is by knowing the amount of carbon that they had at the beginning and then the amount of carbon that you currently have. You can figure out, knowing the half-life of carbon, how long something has been decaying or how many half-lives it's gone through, and figure out how old it is. So it actually is a useful subject to be able to date things like that. Alright, so tomorrow we're going to practice some half-life practice, so come on in prepared, and I will see you then.